Hello everyone, this is Peter Griffin, and I will be presenting the paper Vineyard Properties Extraction, combining UAS-based RGB imagery with elevation data, where UAS stands for Unmanned Aerials. These systems usually consist of drones with a camera attached to them. In recent years, there has been a quest for marginal gains in every aspect of life, and agriculture happens to be one of the most important contributors to the economy of a country. The goal of the farmers is to maximize their yield and the quality of the yield without causing environmental risks, which is easier said than done, as various factors like soil, crop management, irrigation, nutritional status, pest and disease control, and external variables, such as the climate, play an important role in. The stakes are high for everyone here. For the farmers, a decrease in quality and quantity of the yield can result in substantial economic losses, while we might lose out on an amazing glass of wine or grape juice and raisins for people who do not drink. But as we have learned, when the stakes are high, remote sensing always comes to the rescue. In this video, you will learn about a method proposed by Luís Pádua and others which uses UAS-based imagery with elevation data to identify and extract vineyard vegetation by distinguishing it from soil, canopy shadow, and eventual inter-row vegetation, detect vine rows for a given vineyard plot, and estimate possible missing vines. This cost-effective method, which uses as few parameters as possible to achieve these goals, was quite effective, as we will find out. This work was supported by the RDF and North 2020 North Regional Operational Program as part of Project Innovine and Wine, Vineyard and Wine Innovation Platform. Before we dive into what, whys, and hows of this method, we will have to understand a bit more about the study region. So, hop onto the airplane with me, as we are going to Portugal. Now, we are in Portugal. This place is famous for its steep vineyards, killer wine, and Ronaldo! The study site was in northeastern Portugal, and managing vineyards here isn't easy. The terrain's uneven, vines go missing, and growth conditions vary wildly. Imagine trying to monitor thousands of plants across slopes that look like a Stairmaster workout. To tackle this, researchers used a DJI Phantom 4 drone, a lightweight UAV with a 12.4 megapixel camera, a stabilizer for smooth shots, and GPS to keep everything pinpoint accurate. The drone surveyed 3 vineyards. Vineyard A was a non-commercial plot, which was messy and full of gaps. They studied 11 plots were from Vineyard A. Vineyard B was a commercial vineyard, which was neat, organized, and well-managed, the overachiever of vineyards. Vineyard C was another commercial vineyard, which contained a lot of shadows, which affected the pictures taken by the drone. The drone flew in a double grid pattern at 60 to 80 meters high, snapping RGB photos with 70 to 80% overlap to stitch together perfect three-dimensional maps. Using Pix 4D Mapper Pro, the team turned those photos into orthomosaics, digital surface models or DSM, which shows the ground and the vines, and digital terrain models or DTM, which shows just the ground. These maps made it easy to spot vines compared to dirt, weeds, or shadows. For separating the vineyard vegetation from the surroundings, there were 2 main steps involved. The first step was separating the vegetation using vegetation indices, and the second step was separating the vineyard vegetation using the elevation data. The first important part of the method was to separate the vegetation from the surroundings using vegetation indices. The separation of vegetation was done in 4 steps using vegetation indices, which can be calculated by simple arithmetic calculations using the bands from a multispectral image. The first step was calculating the vegetation index, which resulted in a grayscale image. The second step was converting the grayscale image into a binary image using Otz's thresholding method in this case. The third step was to filter the binary image to remove the small clusters of pixels that are unnecessary. These 3 steps have been explained in this picture. The last step was comparing this processed image with an image that was manually segmented. Following this, each pixel was categorized into one of these 3 categories. Exact detection, if the pixel was correctly detected. Under detection, if a pixel containing vegetation is not detected in the processed image. Over detection, if a pixel not containing vegetation is detected as a pixel containing vegetation in the processed image. These steps were performed for 13 different indices, but the index that resulted in the highest accuracy was G% or green percentage index, and the formula can be seen here. Separating the vegetation was just a part of the puzzle, but the major task ahead was to separate the vineyard vegetation, and the next section will talk about how that was done. The second main part of the method involved using the elevation data to separate the vine vegetation from the rest of the vegetation. A crop surface model was created by subtracting the digital terrain model, which represents the bare ground elevation, from the digital surface model, which includes the terrain and all above ground objects such as vine. This process isolates vine vegetation heights that range between 0.5 meters and 2 meters. A range chosen because it represents the average height of vine vegetation in the study region. This approach filters out low-growing weeds as well as tall obstructions like canopy. Finally, the vegetation mask was produced by combining the thresholded vegetation index with the crop surface model outputs, followed by applying morphological operations to remove noise and small clusters of pixels. This step effectively resulted in the separation of vines from the rest of the vegetation. The next step is vine row reconstruction, which addresses fragmented clusters caused by shadows or missing vine. The dominant row orientation is calculated by averaging the angles of the major axes of the detected clusters, with these angles derived from the cluster's elliptical shape. A linear structuring element aligned with this calculated orientation is then applied using a process called morphological dilation, which merges disconnected clusters into continuous rows. This technique ensures that fragmented vine segments are reconstructed into geometrically accurate rows, even in fields that have irregular management. Finally, each pixel in the Vineyard image is examined. If a pixel belongs to vegetation and is inside the vine row area, it is classified as vine vegetation. These areas are then checked for gaps, which are flagged as missing vine vegetation. If a pixel is vegetation but outside the vine rows, it is classified as inter-row vegetation. Once all areas are identified, their total size is calculated. This is done by counting all the pixels in each category, including vine rows, vine vegetation, missing vines, and inter-row vegetation, and then multiplying by the squared ground sampling distance value. This helps create an accurate map of the vineyard, giving viticulturists a clear understanding of the layout and health of the vines. Now that we have a good understanding of how the vine vegetation was separated, the question that comes to mind is how effective the method was. For validating the suggested method, the authors applied this method to 16 plots over 3 vineyards. The results of this method were compared to 8 manually segmented pieces of lands that were randomly selected from these vineyards. These pieces of land were selected in a way that there was diversity in terms of rates of missing vine plants, rows orientation, and inter-row vegetation. In total, 7 parameters were selected for evaluation of the vine rows in the processed image compared to the manually segmented image. The parameters were as follows. Good detection. The row was detected with a high overlap when compared with its real position. Misdetection. The row was not detected. Extra detection. Wrongly detected vine row. Over-detection. The row was classified in multiple vine rows. Under-detection. Multiple vine rows classified as one row. Larger detection. Row is larger than its actual size and smaller detection. Vine row is smaller than its actual size. Using the proposed method, the authors were able to detect all the rows with a mean value of 93.4% accuracy in terms of their position. Out of the rows that were detected, 2.67% of the rows were classified as larger detection and 2.88% of the rows as smaller detection. When the processed image was compared with the manually segmented image, the detected vegetation, which included everything, was estimated to have a mean value of 99.7% accuracy for all the plots combined. When the images extracted by the proposed method were compared with the manually segmented image, the method achieved a 94.1% mean percentage of exact vine vegetation detection, a mean value of 2.93% regarding overclassification, and 2.97% of underclassification. The missing vine vegetation also achieved a good accuracy of 97%. The authors also showed that the processing time of the images is not related to the size or the number of plots, but the characteristics of the area. The processing time spent in each vineyard was as follows: 8 minutes and 45 seconds for Vineyard C, and 5 minutes and 32 seconds for Vineyard A, noticeably in Vineyard B. The method took about 47 seconds to complete the analysis due to the lower number of plots, and the lesser amount of images detailed due to the higher flight altitude that results in a lower ground sample distance. In summary, this study showed that low-cost UAV technology can provide detailed vineyard analysis using consumer-grade drones and RGB imagery. The method effectively identified vegetation, vine rows, and missing vines, making precision viticulture more accessible and cost-effective. It offers real-time, data-driven insights to optimize yield and reduce manual inspection efforts, while remaining economically feasible and efficient. However, challenges remain, including shadow interference, misclassified stressed vines, and overdetection from dense inter-row vegetation. Future improvements could integrate multispectral and thermal imagery to detect vine vigor, water stress, and disease. Expanding to multi-season monitoring would help track growth, environmental stressors, and yield variability. Automating precision agriculture with UAVs, robotics, and AI could further optimize irrigation, disease control, and harvesting. And let's be real, if this makes wine cheaper, we all win. More tech means more wine, and more wine means getting drunk for less.
And it's good for the environment.